if you have a ground like this, okay, and this is a general concept. If you have a current going into the electrode at this point shown there, then the current, this current will move into the soil to an infinite, let's say here, infinite plane or remote, which is voltage is equal to 0. So the current will go all the way to that point where the voltage becomes 0. So the maximum voltage will be at point X, and the minimum voltage will be at point 0. Now, you can actually simulate the whole current flow and the whole soil into a series of resistance like this. Okay, and the current will flow inside there. Okay, same current will flow. And when the current flow inside there, there will be a voltage drop at every point the current flow. So from Vx, it goes to V0. Okay, so Vx is maximum and V0 is minimum. So you can actually draw a profile of, voltage like that. Okay, so maximum voltage is at the top there, and 0 voltage at the bottom. So because we consider the equivalent rather than infinite towards the left and right, it's actually more accurately represented by this structure, which is hemisphere like this. Okay, so the voltage profile will be like this. And the maximum is here again, and the minimum, if you like, is here, V0, Vx, V0. So you can see the minimum is at 0 there, and maximum is at both ends, left and right, because we just make the infinite soil, infinite plane into a hemisphere, because there will be a voltage drop to 0 on the surface as well, rather than infinitely voltage everywhere. So you can see the voltage is reducing in step like that. So if you have a current flowing like this, I, you will have that voltage. Similarly, if the current is actually negative I, you will have the same voltage drop. But of course, the voltage will be minus Vx there and 0 at the end. Understand?
Can you repeat again? What?
So meaning to say, if the current now, if the current now is actually negative I, so here also negative I. So the voltage will be negative I times R. R is the whole thing up to 0 here. But it will reduce to 0 at the end. So negative IR, here V0 is equal to 0. Okay? So meaning to say, if the voltage is negative, so the if the current is negative, the voltage is negative. So any current into the soil will produce this green profile, voltage according to the current flow. You understand?
Okay. Also, that means the Vx has lower voltage potential than
of course.
V0.
It's just because current is negative. Current negative means the current is flowing the other way. You're right?
Okay.
Yeah. So it's like if you talk about potential, you have zero height there, and you have minus height there. So high is here, pressure is very high, so the water will flow down. But if you dig a hole inside the soil at negative H, the water can still flow down because of the height. You see, because of the height negative now. So water which is on the surface of the soil, we still can go down into the soil if the pressure are different. So actually the voltage here will be negative. Voltage is zero and here positive, if you like. That's the current. Now, but in our case, the on the surface the current enters. So the voltage, if the current is positive, then at the remote electrode is zero. But now if the voltage is current is negative, then the voltage is negative to the remote point, which is zero.
Okay. Professor,
Yes.
I still cannot that last time where we stopped that 0.62 from the that 0.62.
What's that 0.62? What is it?
Last time you asked us to prove it, right?
Ah, okay. So now I'm going back to that. Now,
okay.
Can you see the PowerPoint now?
Yeah, can.
Okay. In this PowerPoint, you can see the fall of potential method has 3 electrodes, and you need to prove that V divided by I, which is a measured resistance, which is V divided by I, is equal to the true grid resistance, which is a session grid at point E there, only and only if you made the distance between E and P, which is X, is equal to 0.168 D, which is between E and C, the current probe. Now, I have started the showing. So you can see there are 2 currents there in this structure for our configuration of fall of potential. The first current is actually entering here at point E. Oops, sorry. Entering at point E. Entering at point E. So that is actually a positive current. But the one that entering at point C can be considered a negative current, if you like. Negative current means if it goes in, it negative current. Okay, so because of that, as I said just now, any current that that goes in will produce voltage profile. So positive current will produce this profile. Negative current will also produce the same profile like this. You understand? So because we have 2 probes, so for negative current, you have probe P and probe E. Okay, so probe P and probe E will experience the voltage due to the negative current. See, this probe P and this probe E will experience the voltage due to the negative current. At the same time, it will also experience the voltage, both probe E and P, due to the positive current I. You understand?
Okay.
Okay. So, in other words, VE has 2 components, which is VE due to I plus VE due to minus I. Same VP due to I plus VP is like superposition due to minus I. So there are 2 components there. Okay. So what we have done, VE, okay, here VE due to I already done here. we do VP. Okay, VE due to I is here, the first one. VP due to I, on the other hand, VP, which is in the middle, due to I is this. Already calculated here. Like this. So we have due to I. Now due to minus I, we have also VE and VP. So what we have calculated here is VP, which is this one, due to minus I, and VE as well, due to I. We haven't finished that one. Understand now?
Okay.
Okay. If we continue this integration, we will get this answer. Minus I rho 2 pi d minus A. Okay. So now is the time for us to give the answer for VE and VP. Therefore, VE is equal to first due to I, which is I rho 2 pi A, and second due to minus I, which is this one. Okay, and VP is the first one is I rho 2 pi X, and minus I rho 2 pi d minus X at the top here. Okay, so these are the two components for each one of them, VE and VP. Due to plus, this is due to plus current. This is to do plus current for VP. This is minus current. That's why you have minus in the front there. Okay, now, therefore, if you combine, if you want to find VEP now, therefore, because this is the voltage measured by the meter, which is VE minus VP. Here you can see the voltmeter there, actually VE minus VP. So the VE minus VP, you just take the subsection of that terms, the two terms there, you will end up with this formula. I rho over 2 pi 1 over A minus 1 over X. Yes. And then I rho plus, right? I rho 2 pi 1 over D minus X minus 1 over D minus A. Agree?
Okay.
Okay. Now, if you consider where I want to write, okay, let me write here again. VEP is equal to I rho 2 pi 1 over A minus 1 over X plus I rho over 2 pi 1 minus D minus X